Hey everyone, here's another video. This one's going to cover chapter 8.5 and 8.4 from the textbook this week. I am going to start with 8.5 simply because volume is something that we have lightly covered in the previous video lessons. 8.4, surface area, talks about a formula for surface area of a cone that is, the slanted portion of the cone as well as the base of it. It can get a little confusing, and a lot of you are going to simply memorize the formula, which is fine because to actually prove the formula, you'll need grade 12 math for. So I'm not too sad or too upset that you're going to simply sort of use the formula I give you. But I am still going to take the effort to explain where the formula came from in a grade 9 math level. Okay. Uh, for the moment, though, we are going to start with chapter 8.5, so don't think that we are going in the wrong order. It's intentional. Before I forget, the questions for chapter 8.5 are, the homework questions are here, and these questions under it are for chapter 8.4. I'll direct your attention to it once again. So volume. Please recall from the previous video, we've established that the volume of a cone is simply a third of the volume of a cylinder that the cone would fit into. That's supposed to be a cone. Okay, and what does that mean? Well, if you recall, or if you're looking at the formula sheet, the formula for a volume of a cylinder is the area of the circle multiplied by how many circles are stacked on top of each other. Okay, I don't know how many times I have to, I get really excited about this because there is a logic, and I'm hoping some of you might appreciate it simply because up until now you may have had to just memorize the equation without being explained why. And I hope there's a certain aha moment, a certain connection that is made between what you've been sort of listening to your teacher for and then applying and understanding why based on your logic. Okay, stacked height. Okay, so essentially we've already done chapter 8.5 as your lesson. This video is going to focus on some of the example questions. I'm going to take your homework questions and actually do them with you. Specifically, I am going to do numbers 3, 10, and 12 because I think that they can be somewhat challenging. Number 3 is a little more basic. Number 10 is a chapter problem, and number 12 is sort of working backwards. But they all involve this formula right here. The volume of a cone is 1/3 times pi r squared height. So let's try it. If you have your textbook, open it up. If you want to go to the Maya Nelson virtual, I guess, online textbook that they've made available for you during this pandemic crisis, you may do so. You can pause the video and open it up. I'm going to go ahead. Number 3, Wesley uses a cone-shaped funnel to put oil in a car engine. The funnel has a radius of 5.4 centimeters, a slant height of 10.2 centimeters. How much oil can the funnel hold to the nearest tenth of a cubic centimeter? Now, putting oil in a car may not be familiar to a lot of you unless your parents sort of or your guardians do a kind of self-maintenance garage thing. Here's something that might make more sense. Have you ever tried to put water inside a bottle using a funnel? This might be like an activity that you might have done in kindergarten and during class in a sandbox, learning about water play, volume, whatever. I remember vividly because I was so embarrassed of making such a mistake. My eyes were so fixated on the actual bottle, right? My hands, of course, had a jug of water pouring water into the funnel, but yeah, so this was like me being like totally not paying attention to the actual funnel, but I was so focused. I'm like, am I putting enough water? Because as soon as the water fills up, I have to stop pouring water from my hands. But of course, as a child, I didn't realize that because it's a funnel, it's a bottleneck, the amount of water going into the bottle is so little compared to how much I'm pouring in. The water will simply overflow unless you're careful. So I guess the skill behind using a funnel is you have to look at both the funnel and the amount of water you actually put in, or just put the water into the funnel and then sort of wait until all the water starts to empty out into the bottle. Anyways, if you're like me and you're embarrassed, that still remains to this day a mistake that I made as a child, and I don't know why it was so mortifying. It makes so much sense when you're a kid, right? As an adult, it makes so much sense to make that mistake as a child, but when you are the child, man, was that embarrassing. Anyways, the funnel that this question uses is simply an upside down cone. It has a radius of 5.4 centimeters and a slant height, and that's really important, slant height of 10.2 centimeters. That's centimeters. How much oil, in other words, how much oil can this funnel hold? That is the same as saying, what is the volume? What's the volume of this cone? Well, guess what? We have the formula. I'm going to go all the way back up just to give us some space. Volume of the cone is 1 over 3 pi r squared height. And we just plug in the numbers. Try it. In about 5 seconds, once you've tried it, you'll realize you'll come to a problem. I'm going to give you 5 seconds. Pause the video, plug in the numbers, and see if it matches with what I'm going to do in just a sec. 3, 2, 1. If you put in this, you would be incorrect. Sorry to say. Don't mean to discourage you, but you made a very quick and you made an assumption a little too quickly. You assumed that because a number that was given as a slant height, okay, because the word had a height, you might have plugged it into the height location, and that's actually incorrect. This H represents the full vertical 90 degrees height from top to bottom. Okay, it might make more sense if I actually made a cone right side up. The height is top to bottom, right? It is not a diagonal. It is from the floor in a 90 degrees fashion. How high is it off of the floor? Okay, so next question might be, well, how do you calculate that? I'm going to give you 10 seconds. I'm going to give you another couple of seconds. Pause the video and see how you might actually calculate the real height, not the slant height, but the real height. In 3, 2, 1. If you said Pythagorean theorem, you are correct. Please take a look at this. It's a 90-degree triangle. It is a 2D 90-degree triangle that is sort of drawn inside a 3D cone. Okay, you could think about it as, can you imagine a cone-shaped cake? I just took a knife and sort of cut right in the middle of it. Well, it's still a 2D 90-degree triangle. I'm going to take this and flip it. The base of this triangle is 5.4 centimeters, and the hypotenuse, aka the slant height, is 10.2. And essentially, c squared equals a squared plus b squared. Your practice from plugging in the numbers correctly from previous sections will come in handy here. 10.2 is the hypotenuse, so it is the c squared. A squared and b squared could be any of the two sides, so I'm going to leave it at that. And so from here, I will need a calculator. 10.2 squared is 104.804 equals 5.4 squared, 29.8 0.16 plus b squared. And b squared would therefore be isolated if I subtract both sides by 29.16. That will leave us 74.88. That means b is going to be, of course, I'm going to be a little technical. It's going to be plus or minus 8.6533. And you know why if you've been following my videos. However, does it make sense for a length to be a negative value? No. So that means negative 8.65 is what we call an extraneous, an extra value, extra answer that counts mathematically, but does not count realistically in this scenario. So now that we have the actual height of this cone, we can plug that back in to our original question, giving us the volume of a cone being 1/3 pi r squared height. You may have noticed that I sort of rounded. Scientifically speaking, it should actually be 8.7, rounding to 2 decimal places. But don't worry too much. For the moment, I will specify what number, what amount of decimals I want you to round it to, if it is important. Well, if it is required of you. Okay. So the volume is going to be approximately 264 centimeters cubed. There you go. Okay. Big take-home lesson, 3D structures. There are situations where you'll have to dig deep and look back into previous unit material, such as the Pythagorean theorem, especially for things like cones and pyramids, which I'm sure you would have guessed. In a quick sec, I am going to clear this entire screen and get to question 10. So pause the video if you need some copying, and 3, 2, 1. There you go. So this is going to be page 455, number 10. Number 10 is a chapter problem. I asked you to refer to question 11 in the previous section to determine the volume of concrete in Emily's bird bath. Round your answer to the nearest cubic centimeter. We haven't done that. So I'm just going to draw the images and then try to answer to the best of our ability. Okay? Determine the volume of concrete in Emily's bird bath. Actually, maybe I do. I understand the question seems like it is giving us 2 pictures. One is a cone that is missing the top portion. Okay. Another is a large cylinder plate or bowl that has a kind of rim on it. And I'm not sure what the question is referring to. Give me a second. This is me going back to 8.4, question 11. It says, Emily obtained a bird bath. She plans to paint it with a glaze so it's weatherproof. The bird bath is constructed of 2 parts, a shallow open-top cylinder with an outer diameter of 1 meter and a depth of 5 centimeters, in which the cylinder sits on. Oh, this is going to be a larger question, a lot bigger question than I thought. Okay, well, either way, all we're trying to do is calculate the total volume. So there is a 1 centimeter thickness I can't draw that very well. So I'm looking for the volume of a piece of a cone. Remember, that piece is missing. And I'm also looking for the volume of a hollow cylinder. This is going to be a bit of a challenge for some of you, but let's get started. All right. It says that the radius is 40 centimeters. The height to the edge is 60, and the height to the imaginary tip is an extra 20, and the radius at which it's actually cut off is a 10. So from 40, it narrowed down to a 10. Let's do the volume of that. And then there is this funky looking hollow cylinder. I'm going to draw it as a larger picture so it makes sense to you. That's better. Like that. So this is basically like a little lip or an edge that you can sort of sit on if you get tired. That's what I'm trying to draw here. Okay, let's try it. The volume of a cone. We only know formulas for volume of a cone. We don't know this sort of cut cone. Pause the video and see how you might be able to calculate just a piece of that volume. Going once, going twice. The volume of the cut cone is going to be volume of the total large cone, as if this part was still there, right? Minus the volume of the small missing cone. It's sort of like you had some chocolate bar that looked like a cone, and then your baby cousin came and just bit off the tip of it, okay? So let's do this. For the large cone, if it was a complete cone, the height would be 80 centimeters. The radius is 40 centimeters. That's all you need. That means the volume is going to be 1/3 pi r squared height, which is that's pretty big. 134,041 centimeters cubed. Okay, so the small cone, same thing. Let's pretend that bit off piece is still around somewhere. The height would be 20. The radius is the piece that was cut. It's right here. It's the same radius as the larger cone cutoff is where the smaller cone would start. It's a 10. So the volume is going to be 1/3 pi r squared height, and that is 2,094.4 centimeters cubed. Okay, and if I were to subtract that, well, the volume of the missing cone is going to be 134,041 minus this, approximately 131,947 centimeters cubed. Nice. The next part is going to be this disc. How do we find the volume of this cylinder? It's sort of like similar to before. I'm going to pretend this cylinder is actually completely solid. And then I'm going to figure out the volume of a smaller cylinder that as if I cut out that piece from it. What am I going to do then? So it's going to be the total volume of this bowl is going to be the volume of the large cylinder minus the volume of the small cylinder. Okay? A couple of pieces of information you're going to need. That is 5 centimeters. So how about I change this to centimeters as well, because we're all doing it in centimeters. And the thickness of that little lip is 1 centimeter. All right, here we go. Large cylinder is, let's see, I need pi, I need the radius of the large cylinder, which is going to be half of 100, 50 centimeters. I need the height of this cylinder, which is given to us as 5 centimeters. 5 centimeters. That means the volume of the cylinder is going to be pi r squared height, which is pi r squared height. And that gives us, let's see, I misclicked, 39269.9, which is approximately 39270 centimeters cubed. Okay, we're going to move on to the smaller cylinder. Okay. The smaller cylinder has a lip of 1 centimeter, and it apparently also has a base thickness of 1 centimeter. In other words, the smaller cylinder is going to have a height of 4 centimeters. Its diameter is going to be 1 centimeter and 1 centimeter on all sides. So essentially, the radius is going to be 98 centimeters. That's enough information. Small cylinder, the radius is 49 centimeters. The height is 4 centimeters. That means the volume is going to be, try that out, times height multiplied by pi. It's going to be 30171.85. Let's just round it to a whole number. There it is. Okay, so if I were to subtract it, the volume of the hollow cylinder is going to be 39270 minus 30172, 9098 centimeter cubed. That means the total volume is going to be this plus that, which gives us 131947, 141,045 centimeters cubed. Let's see, 0, 0, 0, 0, 0, 0. That looks like a large number, but you can basically say that's going to be just under, actually not so bad. Anyways, to create this, we would need 141,045 centimeters cubed of cement is needed. Okay. You could take that and try to calculate a price if there's an extended question. That was a long one. Try that on your own. Just because I did it on this video doesn't mean that you ought to skip it. Give it a shot now that you've seen it being done. I'm going to clear this, so pause the video and copy whatever you need in 3, 2, 1. The last question I want to do with you is page 455, number 12. A cone-shaped funnel holds 120 milliliters of water. If the height is 15 centimeters, determine the radius, rounded to the nearest tenth of a centimeter. The reason I want to do this with you is because there is a conversion between centimeters and milliliters as a volume. So here's another funnel, drawing it upside down. And the total volume is going to be 120 milliliters. If you didn't know basic metric conversion, 1 centimeter cubed is equal to 1 milliliter. So you can say this is actually the same as 120 cubic centimeters. If the height, okay, they also say if the height is equal to 15 centimeters, determine the radius. This is my question. How do we connect these two pieces of information together? Please recall, the volume of a cone has been established as 1/3 pi r squared height, 1/3 of a cylinder. Volume is also given. Try plugging in all the information that they gave you. Volume is 120. Pi is a constant. Radius I don't know, and height is 15 centimeters. Just to color coordinate here, okay? Volume is 120. Height is 15. And the radius, I do not know. But once you plug in all the information that they give you, what do you notice? I have an equation with one unknown. This is solvable. Let's do our best to isolate r. So basic algebra, let's get rid of the fraction first. I'm going to multiply both sides by 3. 360 is equal to pi r squared times 15. I'm going to divide both sides by 15. That gets us 24 is equal to pi r squared. I will divide both sides by pi, giving us approximately 7.64 equals r squared. That means r is going to be plus or minus 2.76-ish, because it's rounded. But again, mathematically, both plus and minus can be possible. However, negative 2.76 in this scenario doesn't make sense because we can't have a height, or we can't have a radius that's a negative value. So this is what we call, again, extraneous, or an extra answer that works mathematically, but not realistically. So radius must be approximately 2.76 centimeters. That was a lot faster than number 10, but that makes sense. Number 10 is a chapter problem. It's supposed to be challenging. Once again, as a reminder, numbers 1 to 12, we've done number 3, 10, and 12, but try it again. This is your homework for chapter 8.5. Yeah, once you've mastered that, or you feel a little bit more confident in it, please check out the video for the next bit, which is chapter 8.4 on the surface area of cones. See you there.